In this video, we're going to talk about how dipole antennas work and how to accomplish impedance matching between the RF amplifier's output, the coaxial cable, and the dipole antenna. We're also going to talk about the modulation process for an RF signal. Now here we're going to be talking about the modulation process. I'm going to use this diagram here to explain to you exactly what is modulation and how it works, okay? Now, you have your voice signal, your voice, and you're speaking to a microphone. This is the frequency of everyone's voice. Our voice is between 20 Hz and 20 kilohertz. So these sound waves are at this frequency between 20 Hz and 20 kilohertz. So we need a high frequency to modulate this signal with. This signal is too low to be sent like this. There's no way we could send it this way. We have to modulate it in order to send it out over the airways. So our signal goes into the microphone. The microphone will convert these sound waves to an electrical signal, which is analog, and this electrical signal would be sent to the modulator. Also, we have 700 kilohertz. This is going to become our carrier frequency. And this is a frequency generator which has our 700 kilohertz. Now 700 kilohertz is 700,000 hertz every second. This sine waves represent 1 hertz. And we're talking about 700,000 of these every second. Now you'll notice that we have our sine waves here as well, but it looks a bit different. That's because this is a higher frequency, so the sine waves are smaller. And if we increase this frequency here even more, you'll notice that these will become even smaller, much closer together, but it's the same sine wave. Now this carrier frequency of 700 kilohertz will be sent to the modulator. Now there are many different types of modulation. There's AM, which stands for amplitude modulation, FM, which stands for frequency modulation, and PM, which stands for phase modulation. Now today we're going to be using AM, amplitude modulation, in our example. Now what I have here is the modulation process that occurs within a modulator. We have our high-speed signal here in red, and we have our electrical analog signal here on top here, right? And we have a copy of that at the bottom. It just turned around 180 degrees to be completely opposite to that one. With amplitude modulation, we use the electrical signal to control the amplitude of the carrier frequency. So if you look over here, this is the output of the modulator. Here you'll see that the amplitude of the carrier's frequency is kept within the amplitude of the electrical signal. Now this output modulated signal is carrying both the 700 kilohertz plus the voice information that was modulated. So when this information is sent to the antenna, if you tune your receiver to 700 kilohertz, you would receive the information that's sent within this modulated signal. Now here we have our AM modulated signal, 700 kilohertz. We call this RF, which stands for radio frequency. Now this AM modulated signal is still too weak to send directly to the antenna. So what we have to do is to send it in to an RF amplifier, radio frequency amplifier. At the output of this amplifier, we will get an amplified signal of 250 watts. It will be the same AM modulated signal of 700 kilohertz at the output. So everything will be the same except for the signal is now amplified to 250 watts, suitable to send to an antenna and broadcast out. Now the higher the power, the greater the distance. For instance, local AM radio stations may use 250 watts for their power, but regional stations that need to go further will use 1,000 watts or even more. Now we have to connect the output of our amplifier to the antenna. We use a coaxial cable. Now The dipole antenna is just two equal length metal rods. They're not connected in any way. They're two separate metal rods. And the inner part of this coaxial cable, which is this inner conductor here, is connected to one side of the dipole, and the outer conductor is connected to the other side of the dipole antenna. Every RF amplifier has impedance on the output. And the impedance of this RF amplifier is usually written on the back or wherever, but I know for a fact that this type of amplifier generally have an impedance of approximately 50 ohms. So the impedance of the coaxial cable needs to be 50 ohms as well in order to have maximum power transferred. Maximum power transferred means the 250 watts will be going towards the antenna, right, and be radiated out. If you don't have impedance matching between the RF amplifier and the coaxial cable, you wouldn't have all of this power being radiated out on the antenna. You will have part of it being reflected back towards the RF amplifier, and this is what they call a standing wave. Power being reflected back, and you still have power being sent out from the amplifier. The two meet and you have a wave in here, and this could actually damage the cable, and under extreme conditions it could also damage the RF amplifier as well. With our RF amplifier having an impedance of 50 ohms, we would use an RG8 coaxial cable, which also has an impedance of 50 ohms, to connect the RF amp to the dipole antenna. So we know the impedance of the RF amp out, and we know the impedance of the coaxial cable, but we don't know the impedance of the dipole antenna. The dipole antenna should have the same impedance of 50 ohms in order to have maximum power transfer. You got to have impedance matching between the antenna, the cable, and the RF amp out. However, we don't know this as yet. In order to calculate this, we need to find out what the wavelength is going to be. The wavelength is here. This is the wavelength, and this wavelength is sent out by the antenna when it's broadcasting. It's 700 kilohertz. This is the symbol for wavelength, which is equal to C over F. C is the speed of light and F is the frequency. Now the speed of light is equal to 299,792,458 meters per second. So we round that off to 300 million meters per second. Now the frequency is equal to 700 kilohertz, which is equal to 700,000 hertz per second. As I said before, this stands for wavelength is equal to C over F, speed of light over frequency. So we have wavelength is equal to 3 times 10 to the 8. How did we get this 3 times 10 to the 8? Well, 3 million meters per second, which is the speed of light. If you take the decimal point from here and bring it back 8 places, this is how we get 3 times 10 to the 8. And this is over 700,000 hertz, right? Which is the frequency. C over F. This is F, 700,000 hertz. And the answer would be 428.57 meters. This is the length of this wave. When this 700 kilohertz signal is being broadcast out to the airways, a wavelength of 428.57 meters will be created. That's the length of the wave. Now, the dipole antenna is half the wavelength. So what you have to do is to divide this 428.57 meters by 2. So the length of this dipole will be 214.29 meters. This is the full length from this end to this end. Both halves together would be 214.29 meters or 702.1 feet. So now we have the length of the antenna. Now we know the length of the antenna required to broadcast our 700 megahertz frequency, but we don't quite know what exactly the impedance is as yet. So that's what we're going to figure out next. The standard height that we would mount a dipole antenna above ground would be half a wavelength, which is the same length of this antenna. This antenna is half a wavelength, which we said before is 214.29 meters. We would also mount this at 214.29 meters. This is a standard height. However, at this height, you will have an impedance of 73 ohms. Not 50 ohms that we need, we'll have it at 73 ohms. In order to get it to be less than that 73 ohms, to get it down to this 50 ohms that we require in order to have maximum power transferred out, we need to lower the height of the antenna in order to get it down to 50 ohms. Now, how would you know when you have it down to 50 ohms is the question. Well, we would use an antenna analyzer to check to see when it's down to 50 ohms. We would actually insert the antenna analyzer between the RF amplifier and the dipole antenna and continue to lower the antenna until the reading on the antenna analyzer is down to 50 ohms. So the analyzer will be right within the circuit measuring the amount of signal that is being reflected back. You see, if you don't have the right amount of impedance, part of your signal is going to be reflected back towards your amplifier, and this analyzer would actually measure the amount of signal that would be reflected back. It will say 1:1 is a rating on the front of the analyzer, right? 1:1 will simply mean that 100% of your signal is being sent and radiated out. Nothing is being reflected back. And the impedance of your antenna should be 50 ohms at this point. If you have 1 to 1.5, it means a little bit of the signal is being reflected back. So it's only when you have 100% of the signal being reflected back is your impedance. It simply means that your impedance of your antenna is equal to 50 ohms. Okay? It's only at that point would you have 50 ohms. So first you will have to do your calculation, get the correct length of the antenna. So you will cut your antenna to the correct length, which is 214.29 meters. You'll make sure your antenna is the half a wavelength away from the ground. So you'll have a point to start at, right? You do your test with your analyzer, you'll notice that you'll get some reflection because it's not the right impedance. So you would lower that antenna until you're getting no power being reflected back, and at that point you know that it is 50 ohms, just like the cable and the RF amp out. So nothing will be reflected back. 100% of your power will be radiated out to the airways. This is Trevor from Telecom Training. If this video has been helpful to you and you would like to see more videos like this one, please don't forget to like and subscribe below.